Welcome. Last week of classes, can you believe that? Ooh, it's scary, but also fun, right? So I love my job, but I'm usually not that sad towards the end of term. It's like my favorite. If you get to be on campus around this time, it is so fun because as soon as classes are done, everyone's just hanging out and everyone's studying for finals and it's crazy, but everyone's doing it together. I don't know, it's probably my favorite time of year. It's the sweet spot of final exam period in April. Yeah, and hopefully you guys get a little bit of a break for the summer too. So you had your test last Thursday, and really good. I've had a look and I'm really happy with those grades, and you guys did really well. So congratulations, nice job. In fact, how about this? Great job. I feel like I always use this one though. Great job on test number 2. So I usually like to take some time and do some final exam review. However, I also want to wrap up this textbook and finish chapter 7, which is on unsupervised learning, and that's kind of cool. And so what I want to do is just take this week to finish chapter 7. And then what I want to do, because our final exam is not until April 28th, so that feels like a way off in the distance type of deal. And I'm sure you have a long list of other things that you need to do. Okay, so what I want to do is I want to schedule a final exam review closer to April 28th, where I'll basically just walk you through just some of the questions that we've covered so far, especially those applied questions that you'll need to know for the final. But in the end, my final exam review is this. Consider it test 1 and test 2 and the assignment from chapter 7 all smushed into one. That's basically it. Okay, and so nothing really crazy here, right? But there is that time limit, of course, and some of these take longer than others. But so just buckle up and you can do it, right? You've been doing really well. You guys as a group have been doing really well on test 1 and test 2. And so I want to see that happen for the final exam as well. So I'm not changing anything too drastically. Okay. So the final exam is on April 28th. I think it's late at night. From 6 to 9 PDT, it's online. I'm still deciding if I want to watch you guys. I guess I'm being recorded. I don't really care so much. But maybe just to check that box so I can report to my colleagues that I did watch you guys. Maybe I'll set something like that up, but I'll let you know closer to. Yeah, you can fall asleep, but that doesn't matter. You'll just need to work faster if you're going to fall asleep. So what I want to do is the final exam will essentially be test number 1, test number 2, and the assignment for chapter 7 all combined. So nothing crazy so far, right? I haven't thrown anything out of left field here. I think it's been pretty reasonable, and judging by your grades, I think it has been. So I'm going to keep the same pace. Okay. What I might do, I am open to hosting a final exam review session closer to the final exam. But you'll have to let me know when would be good and if you're even interested. Okay, so let me know if you would be interested. And maybe what I'll do is I'll put a Moodle poll up. Let me know if you would be interested. I'm not going to share anything groundbreaking. I feel like you've got it all covered for test 1 and test 2. So there's nothing really material wise, but maybe just the layout and the types of questions to expect. So let me know if you would be interested. And if so, what day and time through the Moodle poll, which is not posted yet. I just came up with it. I don't have it posted, but I will. Okay. April 28th is so far. I've got a lot to do before then. Okay. And so do you. I know you do. I know you have reports and crazy stuff going on. Okay. Okay. So, anything else I wanted to add before we get going into chapter 7? I don't think so. So what we've talked about so far, and let me see. There was something I wanted to just check quickly. Okay. I lost it. Oh well. So you can use the tests. So you'll be able to use those in practice mode. So you can use those for practice, and that'll be good, right? And then just that assignment. Right. Awesome. Yeah. I won't put together one because I am just going to take all those questions and smush them all together. Too easy if I make a practice one. Okay. Good. All right. Chapter 7 is the last chapter, and we did it, right? Here. By the end of this week, you'll have conquered this whole textbook, more or less, right? We kind of floated through some parts, right? We didn't get into some of the nitty-gritty harder stuff, and that's okay, right? But overall, I think we're going to have a really good overview of all the things that a data scientist should know, right? And you've got the code, right? You've got the code that you've downloaded for the book because I showed you how through GitHub, right? And so you should have the code and you should have everything, and then you can use that in the future, okay? Or at least to guide you. All right, so chapter 7, here we go, is called Unsupervised Learning. I think most of you know Stephen Brown, and we share an office, and we always joke about unsupervised learning as the best kind of learning, because that means we don't have to do anything, right? You guys are just doing unsupervised learning, but that's not really, it is kind of what is going to happen, right? But now we're talking about data, right? And so the difference between supervised learning, which we've covered so far, and unsupervised learning is that unsupervised learning, you give it a data set and you don't even necessarily have an outcome variable that you're interested in. You just want to see, hey, are there any usually we're looking for clusters, right? Is there any way that I could kind of lump this data or group this data in kind of a natural way, right? So we let the data lead the way, essentially, as opposed to in supervised learning, when we build a regression line, right? We are in charge of one, deciding what the outcome is, right? What's the variable I'm trying to predict? And what predictor variables are going to be in my model, right? And so that's very supervised, right? You have to tell it what goes into this model. Same thing for classification, right? What am I trying to classify? And how am I going to do it? What type of model am I going to use, right? Am I going to use logistic regression or something else? Usually logistic regression. And then in chapter 6, we talked about machine learning, which is also supervised techniques, right? But this is where we kind of bridge into the unsupervised learning. So we talked about trees, we talked about k-nearest neighbors, right? But all of those rely on us specifying an outcome that we're interested in, right? And potentially including or excluding predictors that we want in our model, right? And so now for unsupervised learning, we just kind of release the data, so to speak, or at least in my mind, I'm kind of like, here's my data, what do you think? Right. And so there's a couple of different methods that we could use. So today I want to focus on principal component analysis, so PCA, and also the K-means clustering. K-means clustering is going to be your go-to. I just know it, mostly because it's the most intuitive. Okay, I think principal component analysis is a little bit harder, at least for me, to wrap my head around. Right, K-means clustering, I understand the algorithm right away, whereas the PCA, I really had to read this section so many times. Yeah, it's confession time. I had to read it so many times in order to understand it. So if you read it and it doesn't make sense, that's totally normal, right? But in the end, you're going to be using K-means clustering quite a bit, right? Quite a bit more than PCA probably. And so, so we're going to focus on K-means, but I do want to kind of talk about PCA because it is quite different and, in my opinion, difficult. Okay. So unsupervised learning is basically when we're able to extract information from data without specifying a model. So we can extract information from data without specifying a model. Without specifying a model. Okay. And maybe I'll say versus supervised learning, which is from chapters 4, 5, and 6, if you want to be chapter specific to this textbook, right? That's regression, it's classification, which is when the outcome is a categorical variable, right? Regression, remember, is when you have a numerical predictor, and classification is when you have a categorical predictor, typically binary, right? And then in chapter 6, we talked about machine learning, and then it was kind of all bets are off, but usually we're classifying again, right? Talking about a binary outcome and trying to classify that outcome. So it's kind of an extension of chapter 5. It's the progression. Okay, so versus supervised learning, where we need to specify the outcome as well as the predictors. outcome as well as the predictors, or the features, maybe let's call them, but I'll write predictors, right? And potentially even what predictors should be in the model, right? So we have a lot to say and do with how that model performs, right? Because we've told it what predictors to include and which ones not to include, right? And there's no, there are ways to make sure that we're doing the right thing, right? But if we exclude a predictor that should be in there, then our results are going to be quite different, okay? So where we need to specify the outcome as well as the predictors, and even which predictors to include. So we kind of get our hands dirty in there, right? And now for unsupervised learning, that's a way to kind of hands off and let the data tell us and form its own groups, for example. That's kind of cool. That's what K-means clustering is. Okay. So, okay. One thing that kind of happens that to me is not intuitive is this unsupervised learning. Although we're introducing it as this kind of harder thing that we could do, right? Or kind of more large data appropriate thing that we could do, it's really an extension of exploratory data analysis, right? Where we're exploring the data. So for example, if I want to know what my naturally occurring clusters are within this data, if any, right, then I can use this unsupervised learning technique, such as a K-means clustering, for example, right? Because that's kind of the easiest and your go-to probably, or it will be your go-to. And it'll tell me, okay, here are some of the clusters that I've found, and then you can use those clusters as a predictor later on, right? And you can bring it back to the supervised learning, right? Maybe in a regression, you use it as a predictor, right? And so it's really just an extension of the exploratory data analysis, just kind of kicking it up a notch. Yeah. So I'm trying to formulate this sentence so that it actually makes sense. I wanted to say, okay. We can use unsupervised learning techniques as an extension of exploratory data analysis. As an extension of exploratory data analysis. Analysis, which if you haven't seen it abbreviated as EDA before, then that's really common. Exploratory data analysis, that's where we look at the summaries of data. It's not something you would report, right? It's just something that you have to kind of look at to figure out, okay, what is going on with this data, right? So exploratory data analysis is where you look at things like, okay, what's the mean? What's the standard deviation? How many groups do I have? And now we're introducing this this new technique of, okay, if I were to create some number of clusters, for example, how many, what would those characteristics be? Okay. And so we can use unsupervised learning techniques, and I don't think it should be a capital U. I think it's just a lowercase u, that's fine. Unsupervised learning techniques as an extension of exploratory data analysis to help establish clusters in our data, right? For example, right? Can do other things, but usually we're working towards clusters. Okay? Those clusters can be used as predictors, right? Those clusters can then be used as predictors, right? So it can be part of our data. Okay, this observation was in cluster 2. This observation was in cluster 3, right? And so we've generated a new categorical variable that we could use in our analyses, right? Maybe that helps explain some of that variability. Oof. Okay, so let's see here. So we're going to focus today, we're going to focus on 2 techniques. Okay, we're going to talk about principal component analysis, and then we're going to move into K-means clustering, which is kind of my favorite, but also probably your favorite. And it just, I think it's just very intuitive, and so it's what I want to focus on. Yeah. And so today, we will introduce two main clustering techniques. The first one is called principal component analysis. Or PCA. And the second one is K-means clustering. Oops. Well. So K-means clustering is likely the one that you'll use the most. Likely the one you will use the most. One of those reasons is because PCA it can be very tricky to explain, and you'll see why. And so you don't want to have to try to explain that to your client, right? When you could have used K-means clustering and probably pretty reasonably gotten similar results, similar clusters, right? And so it's kind of like, do you want to zigzag through all the blocks to get there, or do you want to just fly like a bird across from A to B type of deal, right? And so it's sometimes we favor the techniques that are easy to explain or easier to explain. So that's why I'm going to say that K-means clustering is likely the one that you're going to use the most. Yeah. There are other techniques, but these are the 2 main ones, and these are the ones we're going to talk about today. And then the rest we'll save for Thursday. All right, so let's talk about principal component analysis. PCA. Okay. I forgot to mention, so I will mention it for each of these techniques, but also I just want to highlight it here because what I'm finding in the textbook is the data that they're using doesn't require standardization. And so they kind of fail to mention it until later, but it is going to be really important that you, whatever clustering technique that you use, you're going to standardize your data first, right? Or at least analyze the deviations right? And so, but usually we just go ahead and standardize the data, because otherwise, like you saw in that assignment that I gave you, right, those large scale variables are going to dominate your means, right? Especially for the K-means clustering. Okay, so be sure to standardize all the variables before either of these techniques. Before using either of these techniques, and I'm gonna bump this down a little bit more. Before using either of these techniques. All right. So now I can put up one. Okay. Okay. One thing about PCA is it requires only numerical variables, right? So here I'm going to say can only be applied to numerical variables. So one of the things you'll want to be careful with is, of course, if you apply it in R and you have these binary variables, for example, then it's going to work, but it's not going to be proper. Okay, and so you'll want to have these just numerical variables, right? Numerical measurements. Okay, so there is a categorical variable component that we'll talk about, but it doesn't really apply to kind of big data situations. So that's why we'll focus on the PCA. Okay. So a couple of things, right? We want to standardize our data, and we also want to make sure that we're only dealing with numerical variables. All right. So PCA combines multiple numeric predictor variables, right, into potentially a smaller set of variables. Okay, and so how it does that is it kind of takes all the existing variables that you have, and maybe you have a lot of variables, right, in your data, and maybe the goal is to reduce the number of variables. We can do that. Okay, but first what we have to do is it considers each of the variables, and then it finds the weights applied to each of these variables that are going to capture most of the variability in your data. Okay, kind of weird, but PCA combines multiple numeric predictors, predictor variables into a smaller set of variables which are weighted weighted linear combinations, and I'm going to clarify what that is below here. Linear combinations of the original set. So you have some original data set, you've standardized all the variables, that's great. And then you have these numeric predictors. Okay. So you have some number of numeric predictors. And then what we're going to do is we're going to build combinations of these weighted, we're going to create weighted linear combinations of the original set. Okay, so when we say linear combinations, what we mean is we're going to create some new variable zi. Okay, so let's pretend that we've got, I want to use the same notation that I have in my notes here, x1 and x2, right? So those are my original predictors. Okay. So I have multiple numeric predictors, x1 and x2. Let's keep it really simple, mostly because, so the reason the textbook starts with 2 is because it's the easiest to visualize, right? I've got x1 and I've got x2, right? I can plot them against each other and then I can see what's going on. As soon as I start to introduce more variables, which we totally can, but then it becomes hard to visualize, right? And so that's why they start with 2, and then they say, well, the extension is you just do the same thing, but you have more variables. Okay, but it's harder. You can't visualize it anymore. So Zi is going to be, is going to be some Wi, so some weight I applied to variable 1, so comma 1, and then I have x1 plus some wi comma 2, which is the weight for variable 2. And maybe this should include the weighted linear combinations, right? And so here, this is the weight for the ith principal component, which is your z principal component, which is your zi. It's a long way of saying zi. Okay, so it's the weight for the principal component that we apply to x1, which is the first predictor variable. Applied to x1, right? The first predictor variable. So here, what we're going to have is we're going to have a linear combination of x1 and x2, and they're going to create some z1, and then we're going to create some z2, and just in general, we're going to create as many z's as we have original predictors. And at least if you're like me, you're thinking, I thought the whole point was I was going to reduce the number of predictors. I was going to reduce the number of variables that I had to deal with. And we will, but what we do is we generate all these zi's for each of the predictors, right? So the idea behind this is that a lot of the time, a lot of the variability is kind of duplicated in each of the predictors, right? And so if we can boil it down to, okay, this linear combination, it shoulders a lot of this variability, then you can use that instead of these individual predictors, right? That's the idea, but I know that's kind of, it's out there, okay? And so here, right, we calculate, and I'm going to say calculate. We don't do any calculations. We let R do it, or Python do it, or whatever, SAS, SPSS, whatever. Right. So we calculate the same number of components, the same, and I'm going to just say same number of Z's as we have predictors in our data. So in theory, each predictor, each original predictor could be replaced by a linear combination of the predictors, okay? But what we can do eventually is we're going to have some final some final Zs, especially if we're making more than 2, right? Let's say we have 10 predictor variables. That's not too many, right? But 10 is still a lot, right? Maybe what we're going to find is that each Z that we produce is not really adding very much, right? It's not really capturing a lot of variability. So then we can start to cut them. Okay, so that's the idea. But we do generate a Z for each of the X's that we have. X1, X2 means that we would generate Z1 and Z2, right? If we have X1, X2, X3, X4, we would have to generate Z1, Z2, Z3, Z4. Now, the holdup on the Zs, and what's kind of interesting is that they have to be orthogonal to each other. Now, orthogonal is just a fancy way, and I will say this, if you've taken linear algebra, there is matrix math going on back here, right? We're not going to do it, right? But if you've taken linear algebra, then that definitely helps, okay? Because then you know what orthogonal means, right? It means that you have these independent vectors. Yeah? And so, let's see here. Let's see. Before I write that down, I just want to talk about these weights, because these are what we call the component loadings. So I just want to jot that down while we're talking about it. But WI1 and WI2 are called the component loadings. Right, and they're really just the weights. Okay. So what we're going to build is we're going to build Z1. Z1 is the first principal component. And to me, it's kind of confusing because principal does mean first, right? But it's the first principal component. First principal component. Okay. Which is going to be the weighted linear combination that best explains the total variation. Okay. And so the first principal component, which is the weighted linear combination, and I'll put in brackets, of the original predictors, but that's kind of understood by now, of the original predictors which is the weighted linear combination that best explains the total variation. Okay. So pretty much what happens is Z1 is going to be your main player, right? And then we have these supporting roles where we say, and I don't have the graph here, but you have the graph in the textbook, and it's going to be a cloud like this, okay? And it's kind of an oval cloud. So for example, if you have it like this, and you've got basically, I'm going to make it more oval. Okay. So Z1 is a linear combination, right? And so it's going to try to explain this variability here, which is the most variability, right? So potentially, right, Z1 kind of explains this variability. And that's a lot of it, right? And so now we've kind of said, okay, well, I've captured that activity. Now I'm going to build another component, another principal component, and I want to capture this other activity, right? There's also a little bit of up down, but the principal component, so the first principal component captures that huge, that kind of largest variation, right? So it covers the most ground. And then we have these supporting principal components that kind of wrap up the other, I guess, the other variability. So what happens is maybe Z2 captures this activity. Okay. And so Z2 is Z2 is another weighted linear combination, okay, but it has to be orthogonal, so it still has to explain the total variation, but in another way, right? And so so that's the key way, or the key thing is that, okay, but it has to be in another way. You can't just keep doing and saying, oh yeah, I'm going to capture all this activity so many times. No, we don't want to do that, because then we don't have these orthogonal components anymore, right? And so then, and orthogonal, I'll write it down, just means statistically independent, and that's kind of the easiest way to think about it. Okay. So Z2 is orthogonal, which means statistically independent is orthogonal to the first component, or the first principal component, Z1. Okay, so it does the same thing, but it kind of takes a different approach, right? So if Z1 goes like this, then it has to go like this. Now, this only works for two variables, right? X1 and X2, right? So X1 and X2, let's say, right? So here I've got X1 and I've got X2, for example. And so now I only have Z1 and Z2. Did I write that down already? Oh yeah. So we calculate the same number of Zs as we have predictors in our data. So that's why for visualizing, we stick to 2, right? And so that's why we only have Z1 and Z2. But if I have a Z3, now let's take it out of the page, right? A third dimension. But I'm not a very good drawer, so I can't do that. That's why we're going to stick to 2. But in general, right, any Zi, right, remember that we're going to generate as many Zs as we have predictors. Okay. And then what we say is that any Zi will be orthogonal to the rest. Okay. And I feel like it's like a little bit blurry. Let me fix it. Try to fix it. Any Zi, right? Remember, we calculate as many Zs, or we calculate as many Zs as we have predictors in the data. Numeric predictors, but let's just say predictors because it's getting crazy. Zs as we have predictors in our data. Right, so any Zi will be orthogonal to the rest of the Zis, right, or Zijs. So will be orthogonal to the rest of the z's. Right? So that means that Z1 is your first principal component. It captures the largest amount of total variation that we can. But then we introduce Z2, so then we go the other way. And then if we introduce Z3, then we go the other way. And then we introduce Z4, and now all of a sudden I can't do it, right? But you can mathematically, right? And so they're just weights, but it also has that restriction of, okay, they have to be orthogonal. So then that dictates the weights. Okay. So we generate as many Z's as we have predictors, but then what we're going to do is at some point, right, even or especially because the Z's are orthogonal to each other, yeah, so if you only have Z1, there's probably not a lot of need for grouping, if we kind of say it that way. So then it doesn't, it's just like a straight line, exactly, right? But really, PCA is when we have a ton of variables and we just don't want to have to deal with so many variables. So we're trying to reduce them and still capture a lot of that activity, right? We still use the information from them to generate these components, but then we can focus on the components. Okay, awesome. Okay, so we generate as many Z's as we have predictors in our data. But then what we do is we can look at how much variability is being captured by each component. And then we might only keep, the components that capture the total, 80% of the variability. So you might have some cutoff, or maybe you're just going to look at it and say, okay, I'm happy with how much activity the first 4 components have captured. And all of a sudden, you've taken information from all your predictors, but you've reduced it into potentially only 4 new predictors. And that's kind of cool, right? It's weird. You're probably going to have to read this section a couple of times before it starts to click, or at least it did for me. The first time I read through it, I was like, but how? And yeah. Needless to say, it's not something that I use in my analyses, but mine are pretty old school, which is mostly supervised techniques anyways. All right. Okay. So we generate as many Z's as we have predictors. As many Z's as we have predictors in our data. It's like the 3rd time I'm writing that down, but it's okay. So we generate as many Z's as we have predictors in our data. But then what we can do is we retain only a portion of them, right? And maybe that's a lot of them, right? If there's a lot of variability that you're trying to capture, or maybe there's some threshold where you're going to say, okay, as long as I've captured 80% of the variability, the total variability, I'm okay with that, right? But so we generate as many Z's as we have in our data, then we retain, right, as many components as are needed to account for most of the variability or most of the variance. Okay, so we generate as many Z's as we have predictors in our data. Then we retain the top predictors, or sorry, not predictors, the top components, let's say. they're going to turn into predictors, but that's not what I meant to say. We retain the top components needed to account for most of the variance, or some threshold variance amount, such as, 80% of the variance has been captured. That kind of brings us back to R squared, right? R squared is what? R squared is the percentage of variability in Y that's explained by the least squares regression line on X. It's very similar, right? It's not the same, but it's kind of, we can use those previous ideas to kind of help us along. And so now we have the same way, but each component is going to account for some amount of data or some amount of variability. And then because they're orthogonal, right, when I introduce another component, I can add that amount of variability that's been captured, right? And then, so if I want to capture, let's say 80% of the variability, if we have a measure of how much variability has been accounted for at each component, we can just add that up, right? And then I can say, okay, well, that in this case, that's going to be the 3 components, right? I can get away with using 3 components, 4 components, instead of maybe 20 predictors, right? That's crazy. And all of a sudden we have this kind of bite-sized modeling situation, kind of going back to supervised learning, right? Where we don't want to have too many predictors to have to deal with. Okay. So to retain the top components needed to account for most of the variance or some threshold amount of variance. Let's finish that thought here. So you're going to have Z1, which is your first component, right? Captures. So let's say, for example, Z1, if it captures 60% of the variability. Right, then maybe Z2 captures 15%. Maybe Z3 captures, let's say 5%. Right, and maybe Z4 captures, I want to make sure I don't exceed 100, but 2%, Z5 captures 2% again, right? And maybe it keeps going and going and going, right? But if we want to have as many components that we can capture 80% of the variability, right? Then we would only need to keep Z1, Z2, and Z3, right? If we want to capture 80% of the total variability, we only need to keep Z1, Z2, oops, that doesn't look like a 2, and Z3. And so that's kind of cool. How come I can just add this up? That's because they're orthogonal, right? And so I can just keep accumulating, right? Good. And each one is going to have to capture less of the variability because Z1 is always going to start by capturing the most. And then Z2 captures the second most, that's also orthogonal, right? And so Z3 captures the third most, which, so the numbers here dictate where the variability is, okay? But I think that's plenty for PCA. So remember that PCA is for numeric variables. PCA is only used with numeric variables. And for categorical data, we can do something called correspondence analysis, but I also want to say that that's really not going to apply in a big data setting, so it's not something we have to worry about. Okay, but just know that it exists, and that's fine. Okay, so PC is only used with numeric variables, and for categorical variables, and maybe I shouldn't say and, because there, for categorical variables, we can use a similar approach. Now, it's not mathematically similar, but it kind of from the surface, it's similar, right? So it looks similar. So for categorical variables, we can use correspondence analysis. I want to make sure I spelled it right. I think I did. But so which is similar. But not very useful in big data settings. Oops. So we'll kind of parking lot that there. Huh? Okay. All right. Now on to K-means. K-means clustering. I think for me personally, K-means clustering is the most intuitive way that I would cluster something. Okay, it is iterative, so so maybe that part my brain wouldn't really come up with, right? But basically what happens with K-means is I do have to determine how many clusters I want. Right, and there are ways that we can determine, you know, the ideal number of clusters. Okay, but the goal is to again minimize the amount of variability within each cluster. Okay, which means what? It means that the clusters are similar to each other if the variability is low. Okay, so if you have just kind of a set of data, let's say, and so a small tiny set, and if I asked you, okay, make 4 clusters, what would be your first thing that you would do, right? Let's say you have only one variable, right? That's nice and easy. Probably what you would do is you would sort based off of that variable. One thing that you could do, and kind of where K-means clustering kind of takes it one step further, is it just says distance again, exactly. As soon as we're talking about variability, right, we're basically talking about distance. Awesome. So what you could do is you could say, okay, I'm going to generate 4 clusters. All right, everyone's just randomly distributed into clusters. And then we calculate the centers for each of those clusters, and then we just move data closer to whatever cluster they should be in, right? And so everyone just redistributes to the cluster with the highest average, sorry, the closest average, right? And then we're able to recompute the averages, right? And then everyone redistributes, right? And finds the average the closest average, the cluster with the closest average to them. And then it keeps doing that. So then we recalculate the average again. And then everyone, if there's any movements that have to be made, right, everyone moves to the cluster with the mean that's closest to them. And notice how everything is just kind of naturally dividing itself up, right, by those averages. So the easiest way to think about it is with one variable, right? And kind of a cute example, right? If we have to take it one step further, a cute example would be with age groups, right? And so let's say you're at a big conference, right? And you're divided up into four groups, let's say. Okay. And they just take the room and they cut it like this. Right, everyone's just divvied into four groups, but then they say, okay, actually move into the group with the closest age to you. Okay, so then you would find, okay, well, what's the average group in my, or the average age in my group? Okay, what's the average age in each of the other groups? Right, and then you would go to the one with the closest average age to you. Right, but then when everyone has kind of moved around, right, then we recompute those averages, and maybe you have to move to a different cluster, right? And so it's not until you stop moving from cluster to cluster that you have this stable cluster, right? And so that's why it's a clustering technique. Okay? And I think it's just kind of really cute to think about all these people going from clusters to clusters, and or observations, I guess, kind of finding their own cluster. Okay, so K-means clustering. You should be using standardized data. There are instances, right, where you might not have to if everything's kind of on the same scale anyways, right? But usually it doesn't hurt to standardize the data, right? And so remember to standardize the data. And I can't quite remember, but I don't remember restriction of categorical versus numeric variables for K-means clustering. I'm pretty sure it has to be numeric because we can only find the means for numeric data, but I don't want to write it down. I'm going to have to check. I feel like I said that last time and I don't remember what it was. I'll have to look back, and now I've got two things to check. Anyways, so let's start off and say that it has to be numeric data, although I'm not going to write it down. Okay, but you have to standardize the data, and the only way to do that is with numeric data. Okay, you have to take the mean, so subtract the mean and divide by the standard deviation for each data point. Okay. So given some desired number of clusters K, given some desired number of clusters K, right? The algorithm for K-means clustering typically goes as follows. And now there are other ways that we could do it, but this is the basic algorithm. Okay, so given some desired number of clusters K, the typical algorithm for K-means clustering goes as follows. First thing, randomly assign all the data points or the responses to a cluster, right? One of those K clusters. Okay. And that's a starting point that might change how you assign these responses to the clusters, and there are different ways that we could do it, but just in general, we just randomly assign them. Randomly assign each response, right? So each data point, each response to a cluster, to one of the K clusters. My head example is 4. K equals 4, but I want to keep it, I'm trying to keep it for K. Randomly assign each response to one of the K clusters. Okay. So then the second step is to calculate the mean of each cluster. Okay. Now, if you're only talking about one variable, then that is the mean, it's the average of that cluster. Okay. But usually we have more than one, right? And usually more than 2 variables, right? And so each variable is going to have some mean. So now we're generating this vector of means, right? And so again, this is one of those things where linear algebra, it really helps to have some linear algebra underneath our belts, but it's okay if you don't. A vector is just a list of information, let's say. Right, so we're going beyond 2D, and we're allowing for any number of predictors. And so we calculate the mean. Oh, that doesn't look like mean. Calculate the mean, which is really just a vector now. Calculate the mean for each cluster. Right, so really what we have to do is the mean for each cluster is going to be a list of each of the means for each of the variables, right? Basically, I'm trying not to use the word vector. Technically, I should be saying vector here, but basically a list of the mean for each variable in the data set. The mean for each variable in the data. So if you only have one variable, then that's easy, right? You can just calculate the average and be done with it. And even if you have 2 variables, it's not that bad to think about, okay, I've got the mean of X and the mean of Y. I can do that for each of the clusters, right? Then when I introduce Z or something like that, it gets a little bit harder to think about. So then once you have these means, then you rearrange the responses or the observations so that they're in the cluster with the mean that's closest to that observation, right? So all observations are relocated to the cluster with the mean that's closest to that observation. So all observations are relocated to the cluster with the mean closest to the observation. Right? When we say closest, you guys have already calculated distances, right? I made you do it by hand, and I know it's tempting to use R, but for a lot of these things, I think it's really helpful, or at least for me, I find it really helpful if I have to work through it by hand, just a mini example, because then I can wrap my head around, okay, what makes sense? So what output makes sense then, right? And that kind of thing. So I find it really helpful, right? But so here, closest, this means that we're going to need some distance calculation, right? And that distance calculation is going to be the squared distances, or we could even use the Euclidean distance because it is. And so let's see here, the closest. This means we have to calculate the distance, right? Distance. Yeah. And usually we can use the Euclidean distance, right? But ultimately, K-means clustering. So here, in terms of the closest, we're trying to minimize, the sum of the squared distances of each record to the mean of its assigned cluster. I had to sneak that in there somewhere. Okay. So everyone just kind of moves to whichever cluster is the closest to them, right? Taking into account all of the variables that we could have, right? And that's why it's really important to standardize, right? Otherwise, these kind of large measurements are going to take over and kind of take over the clusters as well. We've seen that too. Okay. So all observations are relocated to the cluster with the mean closest to the observation, or where it's closest to the mean. So then the fourth thing that we do is we recalculate all the means, right? And then we relocate all the observations, and we keep doing that until the clusters do not change anymore. Yeah, so we recalculate the means, and then we relocate observations. To the clusters closest, and maybe I'll say to the closest cluster. Yeah. And then part 6 is we repeat steps 4 and 5 until the clusters are no longer changing, right? So the observations in cluster 1 stays the same. Even if we've recalculated the means, then everyone is where they need to be. So repeat 4 and 5 until the observations in the clusters do not change. Nice. Couple of final things about K-means clustering, because it's just kind of fun, and I think it's relatively easy to wrap your head around. But one of the things that kind of trips us up is that the sample sizes for each of the clusters are not usually the same, right? So even though we might start with an even distribution across the clusters when we randomly assign them, that doesn't mean that they end up being evenly distributed in the end. Okay, and so most often the sizes of the clusters will not be the same. the sizes of the clusters will not be the same. And that's okay. Oh, I wrote okay the two different ways. And that's okay. How about that? Because K-means clustering, the goal is to find kind of the most separated groups, right? So especially if you have these outliers or extreme observations that you can lump into one group and kind of keep them away from each other, that might be a small group, right? But we're able to separate those out from the other clusters, right? Which would be hard to do, because if you had to have the same size groups, right, same size clusters, you would have to incorporate those outliers into one of your clusters, and that would make a mess, right? And so that's one of the main reasons that you have different size clusters. Okay, so most often the size of the clusters will not be the same, because the main goal is to find the clusters that are best separated. Okay. It looks like I'm all out of time, and that's okay. I'll incorporate it into our review next day. It was just deciding on K, but I think you've all seen the elbow graph that you can use. Sometimes it's not very helpful even. And then we just have to pick a K. Anyways, if you have any questions, let me know. Otherwise, I will see you for our very last class on Thursday. So sad. But then it's summer, so we're happy. All right, I'm gonna stop this here.